In April of 2025, a team of astronomers was searching through infrared images that had been sitting in an archive for more than 40 years. Buried inside the data was a single faint point of heat. When they compared images taken decades apart, the dot had moved, not quickly, not dramatically, just enough to behave exactly the way a distant planet should. Then it disappeared again. If that object is eventually confirmed, it would orbit so far from the Sun that a single year there would last somewhere between 10,000 and 20,000 years. It would spend its entire existence drifting through a darkness so deep that no telescope has ever photographed it directly. And yet the search did not begin with that mysterious dot. It began years earlier when astronomers noticed that several icy worlds at the edge of the solar system were all moving in a direction they should not have shared. The odds of those orbits lining up by chance are extraordinarily small. The simplest explanation is that something massive has been pulling on them for billions of years, something no one has ever seen. Since 2016, some of the world's leading planetary scientists have argued that a hidden planet is quietly shaping the outer solar system through gravity alone. Others remain unconvinced. Every new observation seems to answer one question while creating another. Citizen scientists have searched for it. Some of the largest telescopes on Earth have searched for it. Astronomers have even gone back through decades of forgotten satellite data looking for clues. Still, the darkness refuses to give up its secret. More unsettling still, recent measurements suggest the outer solar system itself is warped in ways that the proposed Planet 9 cannot fully explain. Whatever is waiting beyond Neptune may be even stranger than the planet we set out to find. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. It starts with a handful of distant objects whose impossible orbits forced astronomers to question whether our solar system was ever complete. Before we can follow the faint trail of an unseen world, we need to widen our view of the place we already call home. From Earth, the solar system can appear like a simple collection of planets circling one familiar star. Yet as we travel farther outward together, that picture becomes layered, each region shaped by its own history, its own population of worlds, and its own rules of motion. Closest to the Sun, the 8 known planets occupy a surprisingly modest neighborhood. Mercury circles at about 4/10ths of one astronomical unit from the Sun. An astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers, which is about 93 million miles. Neptune marks the outer edge of this planetary family at roughly 30 astronomical units. Everything we commonly recognize as the solar system fits inside that span. But Neptune does not mark the end. Beyond its orbit stretches the Kuiper Belt, a broad ring of frozen remnants extending from about 30 to 50 astronomical units. Here we find Pluto, Eris, Makemake, and thousands of smaller icy bodies. These objects preserve material from the solar system's earliest days, drifting through temperatures so low that change comes almost unimaginably slowly. Farther outward, the structure becomes less orderly. The scattered disk contains objects that were flung onto elongated paths after repeated gravitational encounters with Neptune across billions of years. Their orbits reach far into darkness before sweeping back toward the distant planetary frontier. Every return tells the story of ancient encounters that permanently reshaped their journeys. The map expands again. Astronomers also propose an even greater realm called the Oort Cloud. This immense spherical shell of icy bodies may extend to nearly 100,000 astronomical units from the Sun. At such staggering distances, sunlight weakens into little more than another bright star. No telescope has directly observed this distant reservoir, yet its existence is strongly supported by the behavior of long period comets that occasionally wander inward. All of these regions emerged from a rotating cloud of gas and dust about 4,600,000,000 years ago, as gravity gathered material into planets, moons, and countless smaller bodies. The outer reaches experienced billions of years of gentle disturbances. According to the standard picture, those countless interactions should have thoroughly mixed distant objects until their orbital directions appeared essentially random. That expectation matters. If the outer solar system followed those predictions perfectly, we would see no preferred alignment, no repeating geometry, and no shared orientation among its most distant travelers. Every orbit would tell its own independent story, with no larger pattern connecting one frozen world to another. But when astronomers eventually examined those remote objects with increasing precision, something unexpected emerged. Instead of complete disorder, several distant worlds appeared to lean together in ways that ordinary chance struggled to explain. We had reached the point where the architecture of the solar system no longer matched the blueprint we believed we understood. Every map has a place where confidence begins to fade. For astronomers, that moment arrived on the 14th of November, 2003, when Michael Brown and his colleagues at the California Institute of Technology noticed a faint reddish world moving through the distant darkness. They named it Sedna, honoring the Inuit goddess of the Arctic Sea, a fitting name for an object dwelling in one of the coldest known regions surrounding our sun. Its discovery seemed exciting enough, but the real surprise emerged only after its orbit was carefully measured. Sedna approaches the Sun no closer than about 76 astronomical units. An astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers, which is about 93 million miles. Neptune circles at only 30 astronomical units. Every familiar explanation for distant icy bodies depended on Neptune's gravity. Yet Neptune cannot meaningfully influence an object whose closest approach remains so astonishingly far away that single measurement unsettled decades of understanding. Imagine placing a basketball at the center of a football field to represent the sun. Neptune would become a tiny grain of sand resting about 30 meters away. Sedna would never come any closer than roughly 76 meters, that is nearly 249 feet, placing it well beyond the edge of that imagined field. The scale reveals just how isolated its journey truly is. Its voyage continues far beyond even that remarkable point. Sedna requires about 11,400 years to complete one orbit around the Sun. At its most distant location, it travels to nearly 937 astronomical units. Sunlight itself needs more than 5 days to cross that immense gulf before reaching its frozen surface. Conditions there are extraordinary. Surface temperatures remain near negative 240 degrees Celsius or negative 400 degrees Fahrenheit. Under such relentless cold, Sedna reflects a rich reddish color that researchers believe comes from complex organic material altered by cosmic radiation over billions of years. Every orbit exposes that ancient surface to an environment almost untouched since the solar system formed. Astronomers searched for explanations. One possibility suggested that another star drifted close to the young sun, tugging Sedna outward during the solar system's earliest years. Another proposed that our sun once possessed a stellar companion whose gravity reshaped distant objects before eventually departing. But a third possibility refused to disappear. Perhaps a massive unseen planet still circled far beyond Neptune, slowly sculpting orbits that otherwise made little sense. For many years, Sedna stood alone, unusual enough to inspire debate, yet isolated enough to remain an exception. Then, in 2012, astronomers identified another distant object, named 2012 Victor Papa 113 and informally called Biden. Its closest approach measured about 80 astronomical units, remarkably similar to Sedna's impossible path. We were no longer studying one peculiar world. We were beginning to recognize a family whose shared architecture demanded a common gravitational story. Mathematics has an unusual habit of noticing visitors before telescopes ever do. Sometimes an equation begins whispering about a world long before any camera records its light. That remarkable sequence unfolded again in January of 2016 when Konstantin Batygin and Michael Brown published a study that challenged one of astronomy's deepest assumptions. They argued that an undiscovered planet was already revealing itself through gravity alone. Their investigation centered on six extreme trans-Neptunian objects. These are distant, icy bodies whose elongated orbits carry them far beyond Neptune's meaningful gravitational influence. Such objects should have been scattered in every direction after billions of years of orbital interactions. Instead, something remarkable appeared. Their closest approaches to the Sun, known as perihelia, pointed toward nearly the same region of space. Their orbital planes also leaned in a remarkably similar direction. That combination demanded attention. The researchers calculated that the odds of both patterns appearing together by random chance were less than 7 thousandths of 1%. Imagine six people standing in six different cities across the world. None has spoken to another, yet every one of them extends an arm toward exactly the same distant point on the horizon. You would immediately suspect a shared influence rather than coincidence. The outer solar system seemed to be displaying that same coordinated behavior, but suspicion alone could never carry such an extraordinary claim. Batygin and Brown built thousands of computer simulations, allowing virtual solar systems to evolve across billions of years. A simulation is simply a detailed mathematical recreation that lets scientists test how gravity shapes moving objects through time. Again and again, one ingredient consistently reproduced the strange orbital alignment. A distant planet traveled on a broad, elongated path, while its gravity slowly shepherded those remote objects into stable patterns over immense spans of time. The proposed world possessed very specific characteristics. Its mass would likely fall between 5 and 10 times that of Earth. Its average distance from the Sun, called the semi-major axis, could lie between roughly 400 and 800 astronomical units. One astronomical unit equals the average distance between Earth and the Sun, approximately 150 million kilometers, which is about 93 million miles. Its orbit might require between 10,000 and 20,000 years to complete, while remaining tilted by roughly 30 degrees compared with the main planetary plane. News of the paper spread rapidly across the scientific community. Researchers who believed the solar system's inventory had been settled suddenly faced the possibility that an entire planet remained hidden beyond every confirmed world. But the strongest feature of the proposal reached beyond impressive statistics. The calculations predicted where additional distant objects should eventually appear if the hidden planet truly existed. Over the following years, astronomers discovered several bodies occupying precisely the kinds of unusual orbits those simulations had anticipated. We had seen this style of discovery once before, when mathematics revealed Neptune before any human eye found it. History seemed to be echoing across the darkness once again. The calculations were complete. Finding the planet proved far more difficult. Once astronomers knew where a hidden world might exist, they encountered an obstacle that no equation could remove. Distance itself had become the greatest adversary, stretching the search into a vast exercise in patience. A planet orbiting between roughly 400 and 800 astronomical units from the Sun would receive only a tiny fraction of the sunlight reaching Earth. 1 astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers, which is about 93 million miles. At those extraordinary distances, any reflected light would be exceedingly weak. Astronomers estimated its apparent brightness between magnitude 22 and magnitude 24. Apparent magnitude is the scale used to describe how bright an object appears from Earth, with smaller numbers representing brighter objects. Those values are astonishingly faint. An object at magnitude 22 is roughly 40 million times dimmer than the faintest star visible to your unaided eyes beneath an exceptionally dark sky. Magnitude 24 is dimmer still by another factor of about 6. Modern observatories can detect such faint points of light, but only after collecting photons from one small region of the sky for many minutes, sometimes much longer. But brightness was only one challenge. The predicted search area covered roughly 2,000 square degrees of sky. That equals examining about 10,000 full moons, one tiny field after another. Every exposure required careful processing before another neighboring patch could be examined. Even the world's largest telescopes could only explore this enormous region gradually. Movement offered a small advantage. Planet 9 would drift across the sky by only about 3 arc minutes each year. An arc minute is 1/60th of a single degree, an extraordinarily small angle. Across an entire decade, that motion would remain smaller than the apparent width of the full moon. Background stars would appear fixed, while the planet would creep almost imperceptibly between carefully separated observations. Recognizing that faint motion demanded remarkable discipline, astronomers compared images taken months or years apart, searching for one tiny point that refused to remain perfectly still. Success depended as much upon timing as telescope size, but our own galaxy complicated the effort. Along the crowded plain of the Milky Way, countless stars and glowing clouds flooded infrared detectors with background light. Against that overwhelming backdrop, a distant moving planet could easily disappear into the surrounding confusion. The National Aeronautics and Space Administration had already completed 2 complete infrared surveys of the sky using the Wide Field Infrared Survey Explorer before the mathematical prediction appeared. Researchers quickly examined those observations. The data excluded hidden planets as large as Jupiter across enormous distances, and Saturn-sized worlds across much of the outer solar system. Yet a colder object resembling Neptune or a super-Earth could still remain beneath the survey's detection limit. But that result redirected the hunt rather than ending it. The search expanded toward the largest ground-based observatories, while astronomers also turned their attention to forgotten infrared records collected decades earlier, hoping that time itself had preserved the evidence they needed. Sometimes the most valuable discovery is not a new observation at all. Instead, it emerges when forgotten records are viewed through an entirely different question. That realization reshaped the search for the hidden planet, sending astronomers backward through decades of archived observations instead of farther outward with newer telescopes. In 1983, the National Aeronautics and Space Administration launched the Infrared Astronomical Satellite, the first space observatory to map the entire sky in far infrared light. Infrared light is heat radiation, allowing instruments to detect cold objects that emit very little visible light. The mission remained active for only about 300 days before exhausting the liquid helium that kept its detectors cold enough to operate. Its brief lifetime proved remarkably productive. During those months, the spacecraft cataloged more than 350,000 infrared sources across the heavens. Many represented familiar stars, galaxies, and clouds of dust. Others remained mysterious because astronomers lacked enough information to identify exactly what they were. The archive endured long after the mission ended, preserving observations whose importance had not yet been recognized. More than 2 decades later, during 2006 and 2007, the Japan Aerospace Exploration Agency launched another infrared survey called ACARI. Using improved instruments with overlapping infrared wavelengths, the spacecraft produced a second map of the entire sky. Between the two missions stretched a gap of 23 years, but that gap became the experiment. A distant planet moving only about 3 arc minutes each year would slowly change position over those decades. An arc minute is 1/60th of a degree, an extremely small angle. Across 23 years, such a world would shift somewhere between roughly 42 and 70 arc minutes, enough for astronomers to recognize that the same object had appeared twice in different locations. Instead of attempting to detect the planet during a single observation, researchers could allow time itself to become part of the measuring instrument. Two faint infrared points, separated by decades yet matching the predicted motion, might reveal a hidden world that neither spacecraft could confidently identify on its own. In April of 2025, Terry Long Fan of National Tsinghua University in Taiwan led the first systematic search using this elegant strategy. His team compared every plausible pairing between the Infrared Astronomical Satellite Archive and the Akari catalog. The search began with roughly 2 million possible matches scattered across the entire sky. Most candidates disappeared quickly. Researchers removed objects whose motion failed to match predictions. Others displayed infrared colors inconsistent with an extremely cold distant body. Known stars and galaxies were discarded by comparing additional catalogs until only 13 candidate pairs remained. But the final step resisted automation. Every surviving possibility required direct visual inspection by experienced astronomers. Human judgment remained surprisingly valuable, distinguishing genuine moving sources from accidental alignments that sophisticated computer algorithms still struggled to separate when the signals became so faint. Imagine reducing millions of possibilities until only one remains. That was the position facing the researchers after every remaining candidate had been examined by hand. 12 vanished under careful inspection, revealed as unrelated infrared sources that only appeared connected through coincidence. One faint candidate refused to disappear. It occupied a region within the constellation Eridanus, a long winding pattern across the southern sky whose name comes from the mythological river of the underworld. Among countless stars and distant galaxies, one subtle infrared source displayed exactly the sort of behavior the search had been designed to uncover. The archived images told an intriguing story. In the Infrared Astronomical Satellite Survey from 1983, a faint source appeared at one precise location. When astronomers examined the corresponding position in the Akari survey from 2006, nothing remained there. Instead, another faint infrared source appeared about 47.4 arc-minutes away. An arc-minute is 1/60th of a degree, making this shift extremely small across the sky. Yet over a span of 23 years, That displacement matched the expected motion of the hidden planet remarkably well. But position alone could never be enough. The object's infrared colors also deserved attention. Observations at wavelengths of 65 and 90 microns suggested an exceptionally cold body. A micron is 1 millionth of a meter, commonly used to describe infrared light. The estimated temperature ranged between 28 and 53 Kelvin, corresponding to approximately negative 220 degrees Celsius or negative 364 degrees Fahrenheit, and negative 245 degrees Celsius or negative 409 degrees Fahrenheit. Those values fit comfortably within expectations for a distant world receiving almost no warmth from the Sunday. Its estimated brightness added another layer of fascination. Assuming a distance between roughly 500 and 700 astronomical units, the research team calculated a possible mass between 7 and 17 times that of Earth. That estimate suggested something larger than the original super Earth prediction, perhaps approaching the scale of Uranus or Neptune. Even so, extraordinary restraint shaped the announcement. The researchers never claimed victory. They described the object only as a candidate, emphasizing that one intriguing signal could still represent background noise, an unusual alignment, or a previously unidentified source unrelated to the solar system. Careful science advances through evidence gathered piece by piece. Confirming such a distant body demanded far more than two observations. Astronomers would need at least 9 separate detections across different times to calculate a reliable Keplerian orbit, meaning a complete mathematical description of how the object traveled around the Sunday. Without that orbital solution, its future position remained uncertain. But the team still searched additional observations collected by the National Aeronautics and Space Administration through the Wide Field Infrared Survey Explorer around 2010. Without knowing the exact orbit, they could not predict the object's location precisely, and no convincing counterpart appeared. Even so, for a brief period during the spring of 2025, this lone moving dot became the most closely watched mystery in planetary astronomy. Discovery in astronomy often arrives through patience. It also depends upon disappointment. Every promising signal must survive repeated examination before it can earn a place among genuine worlds, and this particular candidate soon faced its most demanding test. Astronomers pointed modern telescopes toward the predicted location where the object should have appeared during 2025. If the faint infrared source truly belonged to the solar system, it should still occupy a position consistent with its expected orbit. It would continue moving gradually against the distant background, carrying the same cold signature that had attracted attention in the archival surveys. But the observations produced a different answer. The candidate could not withstand careful follow-up. As additional data accumulated, researchers concluded that the infrared signal was almost certainly not a single distant planet at all. Instead, it appeared to be a chance superposition of unrelated background sources whose combined positions had briefly mimicked the motion expected from Planet 9. The filtering process had removed millions of false possibilities, yet one remarkably convincing illusion had survived. That outcome might sound discouraging. Within observational astronomy, however, it represents an expected stage of careful scientific work. Every search through faint, noisy data produces false positives before genuine discoveries emerge. The challenge is never avoiding those misleading signals entirely. The challenge is recognizing them before they become accepted as fact. The search method had succeeded in exactly that respect. Researchers followed the evidence wherever it led, They proposed only a candidate, gathered additional observations, tested every assumption, and ultimately rejected their own possibility when stronger evidence demanded it. That willingness to abandon an appealing explanation is one of science's greatest strengths, preserving confidence in the discoveries that eventually survive every challenge. But eliminating this candidate also reset the search. At present, no confirmed Planet 9 candidate exists within any publicly available astronomical survey. No observation has yet provided the repeated detections needed to establish a secure orbit around the Sunday. Even so, the investigation left behind something valuable. The comparison between the infrared astronomical satellite and Akari demonstrated that historical infrared surveys can successfully probe the correct distance and mass range where Planet 9 might exist. Time itself became part of the instrument, revealing motions impossible to detect from a single observation alone. Future infrared missions will improve upon that foundation. More sensitive detectors, cleaner calibration, and much longer time baselines will allow astronomers to repeat the same technique using richer collections of observations. Every improvement increases the ability to distinguish a genuine wandering planet from accidental alignments scattered across the distant sky. For a brief moment, one faint point seemed ready to become the solar system's newest world. It crossed every early hurdle before dissolving under deeper examination. Yet the mathematics pointing toward an unseen influence remained unchanged. We were left once again with an invisible gravitational fingerprint, an empty region of space, and a search that had grown more disciplined than before. Scientific ideas become stronger by surviving disagreement. Planet 9 has never lacked supporters, yet its most important critics come from the same community, searching for it. They are experienced planetary astronomers working at leading institutions, and they question the evidence itself rather than the mathematics built upon it. Their central argument begins with the extreme trans-Neptunian objects. These distant worlds appear to share unusual orbital alignments, yet skeptics ask whether that pattern truly exists across the outer solar system. They suggest we may instead be seeing the imprint of our own observing habits, where telescopes happen to look when they observe, and which objects are bright enough to detect. The challenge comes from distance itself. Extreme trans-Neptunian objects spend most of their immense orbits far beyond the reach of present surveys. They become detectable only during the relatively brief period when they approach their closest point to the Sunday. Even then, they must appear within portions of the sky that astronomers have actually searched. Many equally distant bodies could remain unseen simply because they are too faint or occupy regions that have received little attention. But selection effects can create convincing illusions. An observational bias is a pattern introduced by the way data are collected rather than by nature itself. If astronomers repeatedly discover objects only within certain viewing conditions, the resulting catalog may appear organized even when the underlying population is randomly distributed across space. Astronomer Samantha Lawler, working at the University of Regina, led one of the most detailed examinations of this possibility through the Outer Solar System Origin Survey. Her team carefully modeled those observational biases before testing the apparent clustering. After applying those corrections, they concluded that the evidence for alignment became statistically much weaker, suggesting coincidence could explain the existing sample. David Tholen, from the University of Hawaii, raised another concern. Different research groups use different criteria when deciding which distant objects belong in the extreme trans-Neptunian category. Changing those selection boundaries can alter the apparent strength of the clustering itself. If the conclusion shifts whenever the sample changes, confidence naturally becomes harder to establish. But the original proponents remain unconvinced. Konstantin Batygin and Mike Brown argue that newer discoveries, selected specifically to reduce observational bias, continue supporting the same overall pattern. In a paper published during 2021, they analyzed 11 carefully vetted extreme trans-Neptunian objects and reported that the clustering remained significant even after conservative statistical corrections. Their conclusions stayed remarkably consistent despite the stricter methodology. Neither side has persuaded the other. Each newly discovered distant object now carries unusual importance. Some strengthen the argument for an unseen planet, while others dilute the pattern skeptics question. Both outcomes matter equally because they refine the evidence rather than the expectations. We are watching a genuine scientific controversy unfold in real time. The answer will not emerge from louder arguments or stronger convictions. It will arrive through a much larger collection of distant worlds, gathered with carefully measured biases, until the outer solar system finally reveals whether its strange architecture reflects hidden gravity or nothing more than the limits of our own observations. A scientific prediction becomes far more persuasive when nature answers it years later. That is exactly what has kept the Planet 9 hypothesis alive. The earliest distant objects sparked the idea, yet many astronomers place greater weight on discoveries made afterward because those worlds appeared in orbital arrangements the model had already anticipated. One of the first arrived during 2017. Astronomers Scott Shepard and Chad Trujillo announced the discovery of the object known as 2015 TG 387, soon nicknamed the Goblin. Its closest approach to the Sun lies about 65 astronomical units away, while its most distant point stretches to nearly 2,300 astronomical units. Such an enormous orbit carries it far beyond the region where Neptune exerts meaningful long-term control. But surviving there is the real puzzle. Computer simulations showed that the Goblin's orbit remains remarkably stable across billions of years, only if a distant massive planet repeatedly nudges it away from Neptune's disruptive influence. Without that persistent gravitational guidance, repeated encounters with Neptune would gradually reshape the orbit until the object eventually escaped the solar system altogether. The distant orbit itself became part of the evidence. Another surprise followed. During 2019, astronomers reported the object known as 2015 BP 519. Although its distance attracted attention, its orbital tilt proved even more remarkable. Instead of circling close to the shared planetary plane, it travels at an angle of roughly 54 degrees. You can picture the familiar planetary system as a broad spinning disk, while this object slices across that disk at a dramatic incline. That geometry is difficult to explain. Simulations led by Juliet Becker and her colleagues demonstrated that repeated gravitational encounters with a distant inclined planet naturally produce such extreme tilts over immense spans of time. Existing models without Planet 9 struggle to generate such an orbit while also keeping the object gravitationally bound to the Sun for the entire lifetime of the solar system. But another arrival complicated the picture in an unexpected way. During 2025, astronomers announced the object known as 2023 KQ-14, often called Ammonite. Unlike the previously known sednoids, its closest approach pointed in nearly the opposite direction. At first glance, that appeared to weaken the Planet 9 hypothesis. Yet detailed simulations suggested something different. A distant shepherding planet should produce crowded orbital regions separated by comparatively empty ones. Ammonite occupied precisely the kind of opposing location that several Planet 9 models had anticipated. Its long-term stability strengthened that conclusion. Simulations carried Ammonite through roughly 4.5 billion years without destroying its orbit, implying that any hidden planet responsible for the pattern likely circles at least 500 astronomical units from the Sunday. Each discovery expanded the conversation rather than ending it. None proved Planet 9 exists. Yet each arrived after the prediction, and each matched orbital possibilities the hypothesis had already placed on the table. In science, successful prediction earns confidence step by step, because the strongest ideas continue explaining discoveries that did not even exist when the idea first appeared. Sometimes the strongest clue is not found in a distant object at all. Instead, it is written into the orientation of the star we have orbited from the beginning. The Sun appears stable and familiar, yet its rotation carries a subtle imbalance that has challenged planetary scientists for decades. The mismatch is surprisingly small. The Sun rotates around an axis tilted by roughly 6 degrees relative to the invariable plane. The invariable plane is the average orbital plane created by the combined angular momentum of all 8 known planets. In simple terms, it represents the overall flat disk traced by the planetary system as a whole. At first glance, 6 degrees hardly seems remarkable, but the history of the solar system makes that angle unexpectedly difficult to explain. Our planetary system formed from a rotating cloud of gas and dust that collapsed into a broad spinning disk. The newborn sun gathered at the center while planets assembled within that same disk. Under such conditions, you would expect the sun and the planets to retain nearly identical rotational orientations across billions of years. Yet they do not. Astronomers repeatedly tested whether the known planets could slowly shift the solar system into its present arrangement. Their calculations followed gravitational interactions across approximately 4.5 billion years. The outcome remained consistent. The combined influence of Mercury through Neptune simply could not generate the observed tilt. Every refinement returned essentially the same conclusion. But another possibility emerged during 2016. Konstantin Batygin and Elizabeth Bailey proposed that a distant, massive planet traveling on a significantly inclined orbit could steadily reshape the architecture of the entire solar system. Rather than acting through sudden encounters, its influence would accumulate almost imperceptibly over immense spans of time. The mechanism has a specific name. Secular resonance describes a gradual gravitational interaction that unfolds over countless orbits. Instead of producing dramatic collisions or close passes, tiny gravitational pulls add together with remarkable consistency. Over billions of years, those persistent nudges can alter the orientation of planetary orbits without disrupting the stability of the solar system itself. Their calculations produced an unexpected result. A planet with the predicted mass of Planet 9, traveling along an orbit tilted by roughly 30 degrees, naturally generated almost the same 6-degree difference observed between the Sun's rotation and the invariable plane. The agreement was striking because the hypothesis had originally been developed to explain the strange clustering of extreme trans-Neptunian objects, not the orientation of the Sunday. But now one idea addressed two unrelated puzzles. Scientists call this consilience, the strengthening of a hypothesis when separate lines of evidence converge upon the same explanation. It does not prove the hypothesis is correct. Instead, it increases its credibility because independent observations begin supporting one another instead of standing alone. That is why the debate remains so compelling. If Planet 9 is eventually found, the distant world's gravity may explain both the unusual architecture of the outer solar system and the long standing tilt of our own star. If it is ultimately ruled out, astronomers must discover two entirely different mechanisms for phenomena that currently share one remarkably elegant solution. A map can remain accurate while still hiding an unexpected bend. That possibility emerged during October of 2025 when Princeton astrophysicist Amir Siraj and his collaborators examined the distant solar system from a different perspective. Instead of asking whether unseen planets existed, they asked whether the outer structure itself was perfectly flat. Their answer was surprising. The team analyzed the spatial distribution of Kuiper Belt objects, the icy worlds, orbiting between roughly 30 astronomical units and 50 astronomical units from the Sunday. An astronomical unit is the average distance between Earth and the Sunday, extending beyond about 80 astronomical units. The data suggested something unexpected. The outer population appeared tilted by approximately 15 degrees relative to the common orbital plane, followed by the 8 known planets. This was a different mystery. Earlier, we considered the slight tilt of the Sun's rotation axis that involved the orientation of the Sun itself. The newly identified feature described something else entirely, a physical warp in the outer disk of the solar system. Imagine a broad spinning record whose outer edge has been gently lifted while the center remains nearly level. The distant population appears to follow that kind of subtle distortion. But the familiar explanation reached its limit. Computer simulations tested whether Planet 9, with a predicted mass between 5 and 10 times that of Earth, orbiting roughly between 400 and 800 astronomical units from the Sun, could create such a large deformation. Despite its enormous reach, the calculations showed its influence remained too indirect. The distant planet could organize extreme trans-Neptunian objects, yet it could not naturally twist the broader Kuiper Belt by 15 degrees. The simulations pointed somewhere else. Siraj's study introduced the possibility of another unseen world, provisionally named Planet Y. According to the models, this object would be considerably smaller than Planet 9, perhaps somewhere between the mass of Mercury and Earth. It would travel much closer to the Sun, between 100 and 200 astronomical units away, while following an orbit inclined by at least 10 degrees relative to the planetary plane. That distinction matters. Planet Y and Planet 9 represent separate ideas rather than competing identities. If both eventually prove real, the outer solar system contains more than one hidden architect. One would dominate the most distant reaches through immense gravitational influence. The other would reshape the nearer frontier, gradually bending the surrounding population over billions of years. But a closer orbit changes the search itself. Although Planet Y would possess less mass, its predicted distance makes it significantly brighter than Planet 9. That increases the possibility that modern observatories could detect it directly. The ongoing survey conducted by the Vera C. Rubin Observatory reaches into precisely this region, offering one of the strongest opportunities yet to test the prediction against the sky itself. The study did not weaken the case for Planet 9. Instead, it suggested that the outer solar system may contain a deeper gravitational architecture than anyone first imagined, where several unseen worlds together shape the distant landscape through patient influence, extending across the entire age of the solar system. Sometimes the strongest challenge to an idea arrives from the same distant frontier that inspired it. During May of 2025, astronomers announced the discovery of another remarkable outer solar system object. Unlike several earlier findings, this one did not appear to strengthen the case for Planet 9. Instead, it provided skeptics with their most persuasive counterexample yet. The discovery came from a team led by Sihao Cheng at the Institute for Advanced Study in New Jersey. They identified an object known as 2017 Oscar Foxtrot 201, a frozen world measuring roughly 700 kilometers across, which is about 435 miles. That makes it approximately one-third the diameter of Pluto, yet its orbit ranks among the most extreme ever measured around the Sunday. Its path is extraordinary. At its closest approach, the object passes through the inner Kuiper Belt at about 45 astronomical units from the Sunday. At its most distant point, it travels beyond 1,600 astronomical units, reaching almost 5 times farther than the greatest distances predicted for Planet 9. Completing one circuit requires roughly 25,000 years. Across all of recorded human history, it almost certainly remained far too distant for anyone to notice before its recent discovery. But the orbit carries an unexpected message. The orientation of 2017 Oscar Foxtrot 201 does not match the clustered pattern identified among many extreme trans-Neptunian objects. Its elongated path points in a different direction. If Planet 9 truly shepherds these distant worlds through its gravity, then an object spending nearly all its existence in the far outer solar system might reasonably be expected to participate in that same organized arrangement. Instead, it argues back. Astronomer Samantha Lawler noted that this discovery could indicate a more complicated reality. Perhaps the known collection of extreme trans-Neptunian objects remains far too incomplete to reveal the true distribution. What appears today as a meaningful pattern may gradually dissolve as additional discoveries fill the empty regions of the map. From that perspective, apparent clustering could emerge naturally from the limits of where telescopes have searched, rather than from the influence of an unseen planet. Supporters of Planet 9 remain unconvinced. They argue that every large population contains unusual members. A single object with an unexpected orbit does not erase the broader statistical evidence assembled from many independent discoveries. One exception may simply reflect the natural diversity expected in a complex gravitational system that has evolved across the entire age of the solar system. But this distant traveler introduces another puzzle that stands on its own. What process launched a world 700 kilometers across onto an orbit extending beyond 1,600 astronomical units? A close encounter with another star during the sun's youth remains possible. A violent gravitational scattering among the young giant planets could also have played a role. Perhaps an ancient planet, now gone, briefly reshaped the distant frontier before disappearing forever. Whatever the answer becomes, the outer solar system continues revealing objects that stretch every existing explanation, reminding us that the map remains unfinished even where the mathematics appears most confident. Picture a world that no human eye has ever seen, yet whose possible character has already been sketched by mathematics. Before asking whether Planet 9 truly exists, we can ask something equally fascinating. If this hidden planet is real, what sort of place would be waiting beyond the known edge of our planetary family? Current models point toward a category of planet unlike any orbiting our sun today. Most researchers describe Planet 9 as either a super-Earth or a mini-Neptune. Those names refer to worlds larger than Earth but much smaller than the giant planets Jupiter and Saturn. The leading estimates give it a mass between 5 and 10 times that of Earth, built around a rocky or icy interior wrapped beneath a deep atmosphere rich in hydrogen and helium. Its size would be impressive. The planet would likely measure between 2 and 4 times Earth's diameter. Although enormous beside our home world, it would remain modest compared with the largest planets in the solar system. Curiously, this combination of size and mass is the most common kind of planet discovered around other stars, even though our own planetary family appears to lack such a member. But distance changes everything. If Planet 9 circles between roughly 400 and 800 astronomical units from the Sun, sunlight becomes little more than a distant reminder. Its temperature is expected to remain close to 47 Kelvin, or approximately negative 226 degrees Celsius, or negative 375 degrees Fahrenheit. At such extreme cold, the faint warmth escaping from its own interior becomes more important than the tiny amount of energy arriving from the sunday. That lingering heat is left over from the planet's formation about 4,600,000,000 years ago and escapes only gradually through geological time. The view from its surface would feel unfamiliar. The sun would resemble an extraordinarily bright star rather than a blazing disk. It would provide almost no warmth and very little useful illumination. Day and night might appear remarkably similar, with only subtle differences in brightness. If weather exists there, it would likely arise from heat leaking outward from the planet itself instead of energy arriving from above. But another possibility has emerged. During 2025, Amir Siraj, John Chiba, and Scott Tremaine explored an alternative model using an expanded collection of 51 extreme trans-Neptunian objects together with 300 computer simulations. Their results favored a somewhat closer orbit, with an average distance near 290 astronomical units. They also suggested Planet 9 could be denser and more consistent with a predominantly rocky super-Earth than a smaller version of Neptune. That distinction carries enormous consequences. A gaseous ice giant would radiate more internal heat and appear brighter in infrared observations. A rocky super-Earth would remain smaller, cooler, and substantially more difficult to detect. We still cannot say which description is correct. We know neither its color nor its atmosphere. We only recognize the gravitational imprint it leaves upon distant orbits, reading the unseen author through the careful arrangement of its celestial handwriting. Every proposed orbit for Planet 9 leads us toward the same unavoidable conclusion. If such a planet truly exists, it almost certainly did not form where it now travels. The distant reaches between roughly 400 and 800 astronomical units contain far too little material for a world between 5 and 10 times Earth's mass to assemble through the ordinary process that built the known planets. The obstacle is fundamental. In the young solar system, gas and dust became thinner with increasing distance from the sunday. Far beyond Neptune, collisions between icy particles happened less often, and orbital motion became dramatically slower. Computer models show that constructing a planet of this size in that environment would require more time than the universe itself has existed. Whatever Planet 9 may be, it almost certainly began its life somewhere else. But moving such a world presents another challenge. The leading explanation begins close to the giant planets. During the first 100 million years after the Sun formed, Jupiter, Saturn, Uranus, and Neptune were still settling into their modern arrangement. Planetary embryos, the growing building blocks of planets, frequently experienced close gravitational encounters. One of those encounters, most likely involving Jupiter, could have flung a developing giant planet onto an enormously elongated path toward the outer darkness. Normally, that story would end quickly. A planet launched so violently would usually escape the sun forever. Something else had to intervene before that happened. One possibility involves the remaining gas of the young solar nebula. As the wandering planet pushed through this lingering material, gravitational drag could have slowly reduced its orbital energy across millions of years, lifting its closest approach to the Sun into a stable, long period orbit. But another possibility reaches beyond our own planetary family. The Sun was born inside a crowded stellar nursery containing hundreds or perhaps thousands of young stars. During those early ages, neighboring stars sometimes passed within only a few hundred astronomical units of one another. Such encounters were far more common than they are today. A passing star could have gently reshaped the wandering planet's orbit, preventing complete escape while leaving it permanently exiled to the distant frontier. There is an even stranger idea. Planet 9 may never have belonged to the Sun at all. Instead, it could have formed around another newborn star before being captured during one of those close encounters inside the birth cluster. In this scenario, gravity briefly connected two neighboring planetary systems, allowing one world to slip away from its original parent and become permanently bound to ours. A study published during 2017 by Gongji Li and Fred Adams estimated the probability of such a capture at roughly between 1/10 of 1% and 2%. Those odds remain small, yet they are far from impossible, and the resulting orbits resemble those predicted for Planet 9. If that remarkable history proves true, then the most distant planet in our solar system would also be its greatest immigrant, a traveler born beneath another star, spending tens of thousands of years circling a sun that was never meant to be its first home. A new observatory has entered the story, carrying expectations unlike any telescope before it. Perched high in the Atacama Desert of northern Chile, where dry air and clear skies offer remarkable views of the universe, the Vera C. Rubin Observatory achieved first light during the year 2025. With that moment, the most ambitious sky survey ever attempted officially began. Its scale is extraordinary. The observatory's primary mirror measures 8.4 meters across, gathering enormous amounts of faint light from distant space. Behind it sits the largest digital astronomical camera ever constructed, containing roughly 3.2 billion pixels spread across 189 individual imaging sensors. Every exposure captures a field almost 40 times larger than the full moon appears from Earth, allowing vast regions of the sky to be recorded in remarkable detail. But size alone is not the greatest advantage. The observatory was built for repetition. Over 10 years, the Legacy Survey of Space and Time will photograph nearly the entire accessible southern sky once every 3 nights. Instead of producing only a single snapshot, it creates an unfolding record of change. Approximately 10 billion celestial objects will appear in this immense archive, each returning again and again as the survey continues. That rhythm matters. Astronomers call it cadence, meaning how often the same location is observed. Earlier, deep surveys often stared at one region long enough to reveal extremely faint objects, yet they returned too infrequently to recognize worlds creeping slowly across the background stars. Rubin Observatory approaches the problem differently. A distant planet does not need to announce itself dramatically. It only needs to shift ever so slightly between repeated observations. For Planet 9, this strategy changes everything. Its expected brightness falls near the observatory's detection threshold, reaching objects as faint as magnitude 24.5. If Planet 9 occupies the accessible portion of its predicted orbit, repeated observations should gradually expose its motion. What appears to be an ordinary point of light during one visit becomes something different when compared with images taken only a few nights later. But the search is divided between two hemispheres. Current orbital calculations, published by Batygin and Brown during 2024, place the highest probability region near the constellation Orion, which lies mainly in the northern sky. Rubin Observatory cannot fully examine that area from Chile, yet the uncertainty surrounding Planet Nine's orbit extends well into southern constellations, leaving a substantial portion of the possible search region within its reach. Meanwhile, the Subaru telescope atop Mauna Kea in Hawaii continues an independent northern search using its wide field imaging system and powerful 8.2 meter mirror. Separate research teams are scanning overlapping regions with different strategies, reducing the chance that a genuine discovery will be overlooked. For the first time, the mathematical predictions, the observing strategy, and the world's finest survey instruments have begun working together. If Planet 9 truly circles beyond the known frontier, you and we are living through the strongest search ever mounted to reveal it. History has reached this crossroads before, although under very different skies. Long before computers, digital surveys, or giant observatories, astronomers faced another mystery that seemed to exist only on paper. The memory of that success has never faded, and today it remains the closest historical reflection of the search we have been following together. During the early 19th century, the planet Uranus refused to follow its expected path perfectly. As years passed, careful observations showed tiny differences between where calculations predicted it should appear and where it actually traveled. Sometimes it drifted slightly ahead of schedule. Later, it lagged behind. The departures were remarkably small, yet they persisted despite repeated attempts to account for every known influence. Mathematics stepped forward. Working independently, Urbain Le Verrier in France and John Couch Adams in England each asked the same remarkable question: what unseen body could produce those gravitational disturbances? Neither man needed a telescope to begin. Instead, each trusted the laws of gravity, calculating the mass, distance, and position of an unknown planet whose pull could explain Uranus's peculiar behavior. Their conclusions pointed toward nearly the same region of space. On the 23rd day of September, in the year 1846, German astronomer Johann Gottfried Galle received Leverrier's predicted coordinates at the Berlin Observatory. He turned the telescope toward that small patch of sky and compared what he saw against an existing star chart. Within roughly 30 minutes, an unfamiliar point of light revealed itself less than 1 degree from the predicted location. Neptune had been found. It became the first planet discovered through mathematics before direct observation. You can almost feel the confidence that moment gave astronomy. Invisible gravity had exposed an unseen world, proving that careful reasoning could reach beyond the limits of human sight. But history also offers restraint. Leverrier himself later proposed another hidden planet, called Vulcan, to explain unusual motion in Mercury's orbit. Astronomers searched tirelessly for decades. Nothing appeared. The mystery eventually found a completely different solution when Albert Einstein showed that the effects arose naturally from the theory of general relativity rather than an undiscovered planet circling close to the Sunday. That second story matters just as much. It reminds us that successful predictions and unsuccessful ones can begin with equally convincing mathematics. Gravitational puzzles do not always point toward hidden worlds. Sometimes they reveal that our understanding of nature itself requires refinement. Planet 9 now stands between those two historical outcomes. Supporters argue that the evidence resembles the road that led to Neptune, strengthened by multiple independent clues emerging from the outer solar system. Critics answer that astronomy has witnessed persuasive mathematical predictions fail before, and they urge continued caution. But neither history nor debate can provide the final answer. Only observation can decide whether this story becomes another Neptune, another Vulcan, or something entirely unexpected. Imagine the search widening beyond observatories and research institutes until ordinary homes became part of the same investigation. During the year 2017, the National Aeronautics and Space Administration, together with a team of astronomers, opened the hunt to anyone with an internet connection through a citizen science project called Backyard Worlds, Planet 9. Suddenly, the search for a hidden planet no longer belonged only to professionals. The invitation rested on an important scientific insight. Human vision remains remarkably skilled at recognizing motion, especially when faint objects drift through noisy images filled with imperfections. Automated software excels at processing enormous quantities of data, yet tiny moving signals buried among detector artifacts can still confuse even sophisticated algorithms. Our eyes often recognize subtle movement almost instinctively, making thousands of volunteers surprisingly valuable partners in astronomical discovery. Participants viewed short image sequences known as flipbooks. Each sequence displayed repeated infrared observations from the Wide Field Infrared Survey Explorer, showing the same patch of sky at different times. Volunteers simply watched the frames alternate and marked anything that appeared to move. Most changing points proved to be image defects, cosmic rays, or other harmless distractions. But every marked candidate received further examination by professional researchers. The response was astonishing. Within the project's first week, more than 100,000 people from many parts of the world had joined. Eventually, participation grew beyond 150,000 volunteers, representing dozens of countries. Students, teachers, engineers, retirees, and countless curious observers contributed spare moments from ordinary days, each examining another tiny corner of the infrared sky. But Planet 9 remained hidden. That outcome surprised very few astronomers because the survey itself lacked sufficient sensitivity to detect a planet at the predicted distance. Yet, the volunteers uncovered something equally valuable. They discovered dozens of previously unknown brown dwarfs, objects too small to sustain the nuclear fusion that powers true stars, wandering only a few dozen light years from our own solar system. Some were unexpectedly close. Those discoveries revealed that even our nearby stellar neighborhood remained incomplete despite centuries of telescopic observation. Entire worlds emitting faint infrared light had escaped notice until thousands of patient volunteers searched frame after frame with remarkable persistence. The project also produced a valuable collection of outer solar system candidates deserving professional follow-up. More importantly, it demonstrated that distributed human attention, guided by careful scientific design, can become a genuine research instrument. Rather than replacing astronomers, thousands of volunteers multiplied the number of careful eyes available to inspect difficult data. But another lesson quietly emerged alongside the scientific results. The possibility of an undiscovered planet orbiting our own sun captured imaginations across the world in a way few modern astronomical ideas have achieved. People willingly devoted evenings, weekends, and ordinary moments between daily responsibilities to examine faint infrared images, hoping the next moving point might change our understanding of the solar system. The hidden planet has not appeared. Yet the search continues, growing with newer observations and better data. Each careful comparison, each patient volunteer, and each small contribution reflects something enduring about scientific discovery. We advance together, one image at a time, until the darkness finally yields whatever truth it has been holding. Picture a comet beginning a journey so distant that neither you nor any human civilization could witness its full path. Far beyond the familiar planets, tiny gravitational influences accumulate over immense spans of time. Each gentle pull seems insignificant on its own. Together, they reshape destinies measured across billions of years. Planet 9, if it exists, would contribute to that patient process. Its influence would extend beyond the distant objects whose unusual orbits first inspired the hypothesis. A massive planet traveling between roughly 400 and 800 astronomical units from the Sun would slowly disturb icy bodies scattered near the frontier between the Kuiper Belt, the scattered disk, and the inner Oort Cloud. Those regions contain frozen remnants from the solar system's earliest history, preserved in extreme cold since planetary formation. Some of those frozen bodies become long-period comets. A long-period comet is simply a comet requiring more than 200 years to complete one orbit around the Sunday. Many spend thousands or even millions of years far from sunlight before a sequence of gravitational encounters gradually redirects them inward. The giant planets already play the largest role in this process, especially Jupiter and Neptune. But Planet 9 could add another recurring influence, changing the paths of certain objects over extraordinary lengths of time. Its effect would be statistical. No single comet could confidently be traced back to one distant planet. Yet over approximately 4,500,000,000 years, repeated gravitational nudges could alter the overall flow of long-period comets entering the inner solar system. Each encounter would be slight. The cumulative outcome could become significant. Some of those visitors may have carried organic molecules. Others may have delivered minerals containing water locked within their structure. Many struck young Earth while its surface was still changing rapidly. Others merely crossed the sky, becoming brilliant spectacles recorded by ancient civilizations that viewed them as signs from the heavens, centuries before their true nature became understood. But the influence would never remain fixed. Planet 9 itself would slowly precess, meaning its orbital orientation would gradually rotate through space over millions of years. As that orientation changed, the regions receiving its strongest gravitational guidance would also drift. Different populations of distant objects could therefore be redirected during different geological eras, producing a pattern that slowly evolves instead of remaining constant. Can you sense how vast that connection becomes? The planet beneath you and a world that may orbit unimaginably far away would never touch, exchange light in any meaningful way, or share warmth. Yet gravity ignores such separations. It links every mass across the solar system, weaving together countless tiny influences that accumulate through deep time. If Planet 9 is real, then Earth has spent its entire history participating in that invisible relationship, shaped in small measure by a distant companion that no human eye has ever knowingly seen. Sometimes the greatest mystery is not what we discover, but what seems strangely absent. As we widen our view beyond our own planetary family, an unexpected pattern begins to emerge. The solar system that feels so familiar gradually starts to look unusual against the crowded backdrop of the galaxy. That realization came into sharp focus through the National Aeronautics and Space Administration's Kepler Space Telescope. Between 2009 and 2018, It watched more than 150,000 stars, searching for tiny dips in brightness caused when planets crossed in front of them. This technique, known as the transit method, detects worlds by measuring the faint shadow they cast while passing across their parent stars. The results transformed planetary science. Among thousands of confirmed discoveries, one category appeared again and again. The galaxy seemed filled with planets larger than Earth, yet smaller than Neptune. Astronomers call them super-Earths, meaning planets with masses between 1 and 10 times that of Earth. More than 30% of Sun-like stars appear to host at least one such world, making this the most common planetary class yet observed around stars similar to our own. But our solar system presents a puzzle. Earth has one Earth mass. Neptune has approximately 17 Earth masses. Between them lies an enormous gap, precisely where super-Earths are expected to exist. Standard models of planetary formation have never fully explained why our planetary family lacks the galaxy's most common type of world. This absence has become known as the missing super-Earth problem, a reminder that even familiar neighborhoods can contain unexpected questions. Several explanations compete. One leading proposal involves the Grand Tack model, a scenario in which Jupiter migrated inward during the earliest stages of planetary formation before reversing direction and moving outward again. That migration may have scattered growing planetary building blocks, preventing a super-Earth from ever completing its formation close to the sunday. But another possibility carries us back toward the distant frontier we have been following. Suppose our solar system did produce a super-Earth. Suppose it grew alongside the young giant planets before a violent gravitational encounter flung it onto an immense elongated orbit. Instead of escaping entirely, the wandering planet remained bound to the sun, settling into the distant path now attributed to Planet 9. Under that interpretation, the hidden planet would not represent an unexpected addition to our planetary family. It would complete a pattern already seen throughout the Milky Way. The idea is remarkably elegant. A missing super-Earth would no longer be missing. It would simply be extraordinarily difficult to observe, spending most of its existence in regions where sunlight becomes little more than a brilliant point against an endless sky. If that picture proves correct, then our solar system may not be exceptional after all. We may have possessed the galaxy's most common kind of planet from the very beginning, only to lose sight of it across billions of years until gravity slowly revealed where to begin looking. Imagine opening an observatory report one ordinary morning and finding a single faint point of light that refuses to stay fixed among the stars. Night after night, it shifts by the smallest amount. Its motion matches the predictions. Its path cannot belong to any known object. After generations of searching, a hidden planet has finally stepped into view. Everything would change at once. The discovery would mark the first new planet found within our solar system since Neptune in the year 1846. Nearly 180 years would separate the confirmation of the eighth planet from the identification of the ninth. Few scientific announcements could rival the significance of that moment. But detection would only begin the work. Astronomers around the world would immediately turn their telescopes toward the new world. Spectrographic analysis, the technique of separating light into its individual colors, would search for the chemical fingerprints of gases surrounding the planet. Thermal observations would measure the faint heat escaping from its interior, revealing how much energy still remains from its ancient formation. Repeated measurements of brightness would determine how quickly the planet rotates and whether unseen moons periodically cross in front of it. Questions would multiply. Every new observation would refine estimates of its mass, diameter, atmosphere, and internal structure. Researchers would compare those measurements with years of theoretical predictions, discovering where the models succeeded and where they failed. Even unexpected results would become valuable because they would reveal how incomplete our understanding had been. But reaching the planet would demand extraordinary patience. At the current speed of the Voyager 1 spacecraft, approximately 17 kilometers per second, which is about 10.6 miles per second, a spacecraft launched immediately after discovery would require roughly between 30 and 70 years to arrive, depending on where Planet 9 happened to be along its immense orbit. The journey would span scientific careers and perhaps entire generations. Engineers already imagine faster possibilities. Laser-driven light sails, nuclear thermal rockets, and solar sails accelerated during a close approach to the Sun, each promise greater speeds. None has yet matured into a system capable of carrying a dedicated mission across such staggering distances. The technology remains a goal rather than a completed achievement. The planet itself would also await an official name. Until direct confirmation, the International Astronomical Union would not assign a formal designation. Informal suggestions already exist, including the light-hearted nickname Fatty, used by Konstantin Batygин's research group. More traditional proposals draw upon mythologies associated with darkness, distance, and remote realms, reflecting the naming conventions long applied to outer solar system bodies. But perhaps the deepest consequence would unfold more gradually. Finding Planet 9 would strengthen confidence that careful mathematics, patient observation, and persistent testing can reveal realities long hidden from human sight. The empty places on our maps would feel a little smaller, and the universe a little more understandable, because something predicted only through gravity had finally become visible. Science also advances through absence. Sometimes the most valuable result is the one that removes an idea from the map, leaving behind a clearer picture of everything that remains. As our journey reaches this point, we have to allow for that possibility as honestly as any hopeful prediction. The search for Planet 9 cannot continue forever. The Vera C. Rubin Observatory was built to transform uncertain hints into measurable evidence. Across its planned 10-year survey, it will repeatedly scan the accessible southern sky, building the largest catalog of distant solar system objects ever assembled. With enough discoveries, patterns that once appeared persuasive will either become stronger or gradually dissolve beneath a much larger collection of evidence. But suppose no planet appears. If the observatory completes its survey without detecting a world matching the predicted characteristics, and if the growing population of extreme trans-Neptunian objects no longer shows meaningful clustering after observational biases are carefully corrected, then the strongest scientific conclusion would become unavoidable. Planet 9, as currently proposed, would almost certainly not exist. That result would carry remarkable weight. At the observatory's expected sensitivity, any object brighter than approximately magnitude 24.5 across the surveyed regions should reveal itself. Combined with dedicated northern sky searches using the Subaru telescope, only a narrow range of possibilities would remain. Any surviving candidate would need to be exceptionally faint, extraordinarily distant, or located within a very small region that somehow escaped complete observational coverage. But the questions would not disappear. Without Planet 9, every unexplained orbit would demand a different answer. Sedna would still travel along its extraordinary path. The Goblin would remain difficult to explain. The object known as 2017 Oscar Foxtrot 201, would still reach an astonishing farthest distance of about 1,600 astronomical units from the Sunday. Each object would continue asking how it reached such an extreme orbit through processes already understood. Attention would naturally shift elsewhere. Researchers would examine whether observational bias alone produced the apparent clustering. Others would revisit early encounters with passing stars, asymmetries within the young protoplanetary disk, or subtle gravitational interactions unfolding across immense spans of time. The Sun's roughly 6-degree axial tilt would also require a separate explanation that no longer depended upon an unseen, massive planet. But a negative result would still reshape planetary science. Eliminating Planet 9 from the most probable range would strengthen our understanding of how the outer solar system formed, how astronomical surveys can unintentionally create misleading patterns, and where the practical limits of direct observation truly lie. Every improved statistical method, every newly discovered distant object, and every refined model would remain valuable regardless of the final verdict. The search itself has already expanded the frontier. We know far more about the distant solar system today than when the idea first emerged. Whether the final answer is a hidden planet or an elegant correction to our assumptions, you and we arrive at the same destination, a deeper understanding of the remarkable system we have always called home. Imagine widening a map every time you look at it. Each new survey stretches the known frontier a little farther, revealing that what once seemed like the boundary was only another beginning. That has become the rhythm of exploring the outer solar system, where every improvement in our instruments uncovers another population waiting beyond the last horizon. The darkness is crowded. Beyond Neptune lies a vast collection of worlds too faint for a single observation, too slow to reveal their motion over a few nights, and too cold to shine strongly in infrared light. Earlier generations of telescopes simply lacked the sensitivity and the patience needed to separate these distant bodies from the immense background of the sky. But history keeps repeating itself. Whenever astronomy gains a sharper view, the inventory of the cosmos expands. The discovery of the Kuiper Belt during the 1990s transformed Neptune from the apparent edge of the planetary system into a gateway leading toward an entirely new realm of icy objects. Sedna then pushed the structured solar system outward to roughly 76 astronomical units from the Sunday. Extreme trans-Neptunian objects, including the Goblin and Ammonite, have carried that frontier even farther into regions that once seemed almost unreachable. Yet those discoveries may represent only the smallest fraction. Far beyond them, astronomers infer the existence of the Oort Cloud, an immense spherical reservoir of icy bodies that may extend to nearly 100,000 astronomical units from the Sunday. No telescope has directly observed this distant population. Its existence is reconstructed from the paths of long-period comets, whose immense journeys point back toward a reservoir that remains beyond direct imaging. Could that unseen region contain far more objects than we have imagined? The evidence leaves that possibility entirely open. But the individual mysteries no longer stand apart. Planet 9, the proposed Planet Y, the warped outer Kuiper Belt, the unusual orbit of Sedna, and the astonishing trajectory of the object called 2017 Oscar Foxtrot 201 all seem connected by a broader question. What truly occupies the distant solar system, and what sequence of gravitational events arranged those bodies into the architecture we measure today? Answers will arrive gradually, Each newly discovered object strengthens an existing explanation or reveals where that explanation falls short. Statistical confidence grows through accumulation rather than spectacle. Longer observing campaigns, deeper surveys, and increasingly sensitive instruments continue adding pieces that previous generations could never collect. The scientific picture has been expanding for more than 2 decades, ever since Sedna first challenged expectations. But the edge itself has changed. It is no longer viewed as an empty frontier waiting for a single, remarkable discovery. Instead, it appears as a vast landscape that has only begun to emerge from darkness. Every careful search returns more structure, more worlds, and more evidence that the distant reaches of our own solar system remain richer than we once believed, inviting you and we to keep looking with greater patience and sharper eyes. Long before our eyes confirm a discovery, the universe often leaves fingerprints behind. We learn to recognize those subtle traces, then slowly assemble an unseen reality from the motions, distortions, and patterns that visible objects cannot explain on their own. That approach has become one of the defining strengths of modern astronomy. Planet 9 belongs to that tradition. Its proposed existence rests upon inference, the careful process of deducing an unseen object from the influence it appears to exert on everything around it. We have followed this path before, and some of the greatest discoveries in science began exactly the same way. Consider dark matter. Astronomers have never directly detected the particles believed to make up this mysterious substance, yet observations consistently show that galaxies rotate too rapidly for the gravity of their visible stars alone. Light from distant galaxies also bends around enormous clusters more strongly than ordinary matter can produce. Across the largest structures in the universe, invisible gravity appears to provide the framework upon which galaxies assembled. Current measurements indicate that dark matter contributes roughly 27% of the universe's total mass and energy, even though no telescope has ever photographed it directly. But invisible evidence reaches beyond cosmology. In 1930, Wolfgang Pauli proposed the neutrino to preserve the conservation of energy during radioactive decay, years before technology existed to detect such a particle. Scientists finally confirmed neutrinos experimentally in 1956. Today we understand that approximately 100 trillion neutrinos pass through every human body each second, interacting so rarely that almost everyone continues its journey without interruption. Black holes followed a similar path. They first emerged from the mathematics of Albert Einstein's theory of gravity rather than through observation. Decades passed before astronomers gathered convincing indirect evidence, and more than a century separated those equations from the first image of a black hole shadow captured during the year 2019. Mathematics revealed the destination long before instruments arrived there. But inference is not a weaker form of knowledge. It demands extraordinary confidence in the underlying laws of nature. When those laws accurately predict how visible objects should behave, any persistent deviation becomes meaningful. Multiple independent clues begin pointing toward the same unseen cause, each strengthening the others until the invisible becomes almost as compelling as something plainly visible through a telescope. Planet 9 now occupies that uncertain frontier. Several independent lines of evidence have encouraged astronomers to keep searching, while competing explanations continue testing every assumption. That balance remains essential. Good science allows attractive ideas to face relentless examination rather than protecting them from doubt. Whether those converging clues eventually reveal a genuine planet or dissolve beneath richer observations, the process itself demonstrates something profound. You and we have learned that careful reasoning can illuminate places where no light has yet reached our instruments, allowing knowledge to grow from shadows long before certainty finally steps into view. Across continents, different people begin the same evening with the same destination in mind. Some climb mountain observatories, others open laptop computers at kitchen tables. A few compare decades old archives line by line. None can say with certainty that the object they seek is there. Still, the search continues, gathering thousands of separate efforts into one shared pursuit. That tells us something important. Two independent teams of professional astronomers continue examining overlapping regions of the outer solar system with the world's largest telescopes. Their calculations differ in detail, yet both pursue the same possibility with remarkable persistence. Scientific curiosity drives them forward, while another familiar human impulse travels beside it, the hope of becoming the first person to reveal a new planet to history. But discovery has never belonged only to professionals. More than 150,000 volunteers from many countries joined the Backyard World's Planet 9 project, giving evenings, weekends, and spare moments to inspect infrared image sequences from the National Aeronautics and Space Administration's Wide Field Infrared Survey Explorer mission. They expected no financial reward. Most understood they would probably never identify Planet 9 itself. Even so, they kept looking, frame after frame, because contributing to knowledge carried its own value. Their patience changed astronomy anyway. Participants uncovered previously unknown brown dwarfs, objects too small to sustain the nuclear fusion that powers ordinary stars. They also identified promising candidates worthy of professional investigation, demonstrating that distributed human attention remains remarkably effective when guided toward carefully designed scientific questions. Elsewhere, another lesson unfolded. Researchers from Taiwan, Japan, and Australia spent years comparing observations separated by more than 2 decades, searching for faint motions hidden within enormous archives. Their strongest candidate ultimately failed under closer examination, yet they published the work because the search technique itself improved future investigations. Even an unsuccessful candidate became useful knowledge. But perhaps the greatest expression of commitment stands beneath the skies of northern Chile. The Vera C. Rubin Observatory represents an investment of roughly $2,400,000,000, supporting a facility designed to answer countless astronomical questions over many years. Among those questions rests one especially compelling possibility: whether an unseen planet truly circles the distant reaches of our own solar system. Seen together, these efforts reveal how science actually advances. Careers, public funding, private curiosity, engineering, mathematics, observation, and persistence become parts of the same long conversation. Individual contributions differ enormously in scale, yet each supports the next step. History offers many examples of searches lasting longer than anyone expected. Some uncovered exactly what researchers predicted. Others revealed something entirely different. Still others ended by proving that an attractive idea was mistaken, opening stronger explanations in its place. The people working today understand that outcome cannot be guaranteed. Some will retire before the final answer emerges. Graduate students, now examining fresh observations, may eventually provide the decisive evidence years from now. You and we witness only one chapter, while the search itself continues beyond the lives devoted to carrying it forward. Imagine measuring time with an orbit so vast that entire civilizations appear and disappear before the journey is complete. That is the scale we enter When we follow the possible path of Planet 9, our calendars become almost meaningless. Human generations dissolve into moments, while gravity continues its patient work across ages that stretch beyond ordinary imagination. The solar system itself is about 4,600,000,000 years old. If Planet 9 exists, it has circled the Sun somewhere between roughly 230,000 and 460,000 times, depending on the true length of its orbit. Each revolution lasts between about 10,000 and 20,000 years. During a single circuit, continents, climates, and living species can all change beyond recognition. Our story occupies only an instant. The last time Planet 9 would have passed the same point where it may reside today, anatomically modern Homo sapiens had not yet spread across the world. Later, during that same immense orbit, artists entered the cave now called Chauvet in France and painted animals that still speak across deep time. Long before another revolution could finish, agriculture emerged, cities appeared, writing began, and every chapter of recorded history unfolded beneath the same distant gravitational influence. But one earlier orbit reaches even farther back. Before that journey ended, our own species had not yet appeared. Countless generations of other human relatives lived and vanished, while the hypothetical planet continued along its immense elliptical path, changing position almost imperceptibly from one century to the next. Its rhythm belongs to celestial mechanics rather than human memory. Yet its influence, if it exists, never needed urgency. The clustering of the extreme trans-Neptunian objects, meaning icy bodies traveling on extraordinarily distant paths beyond Neptune, would have developed through countless gentle gravitational encounters accumulated across hundreds of millions of years. The proposed contribution to the Sun's tilted rotation axis would have grown through secular torque, a gradual gravitational twisting effect acting continuously over almost the entire lifetime of the solar system. No observer could witness that change directly within a single lifetime. But we can recognize its signature, the span of recorded human history, from the earliest writing systems in ancient Mesopotamia until today, covers less than half of one possible Planet 9 year. Within that remarkably brief interval, you and we have learned enough about gravity to notice subtle patterns among remote worlds, estimate the mass of an unseen planet, predict the shape of its orbit, and identify where telescopes should continue searching. That achievement deserves its own sense of scale. Across billions of years, matter organized itself into stars, planets, oceans, living cells, minds, mathematics, and observatories. From one ordinary world, those minds have begun tracing the outline of something they have never directly seen. Whether Planet 9 ultimately appears or fades from the evidence, that patient act of understanding remains one of the most extraordinary stories our solar system has ever produced. Sometimes a single word survives because no better one has ever been invented. In this story, that word is ghost. It does not suggest fantasy or superstition. It describes a presence revealed only through its effects, leaving traces that point towards something real while refusing direct sight. That is exactly where Planet 9 stands today. In its oldest meaning, a ghost is something recognized through disturbance rather than appearance. You notice displaced objects, altered paths, or patterns that no longer fit. The source remains hidden, yet its influence continues shaping everything around it. Planet 9 occupies that same unusual category, existing, if it exists at all, almost entirely through consequences instead of direct observation. We have never received a confirmed photon from its surface. No telescope has resolved its shape. No instrument has measured its atmosphere. No spectrograph has separated the colors of its reflected sunlight into chemical fingerprints. It has no official name because confirmation has never arrived. Instead, astronomers examine clustered orbits that resist simple explanation: the slight tilt of the sun's rotational axis, the warped structure of the distant Kuiper Belt, and even a promising infrared candidate that ultimately disappeared beneath closer scrutiny. But absence can carry information. Searching for Planet 9 asks us to examine the outline left behind by something hidden rather than the object itself. You and we are reading a gravitational landscape, noticing where distant worlds gather, where their paths bend, and where long term motion hints that another massive body may be sharing the same celestial stage beyond ordinary sight. Astronomy has often advanced this way. Invisible influences revealed planets, black holes, and forms of matter before direct observations strengthened those conclusions. Planet 9 extends that tradition into familiar territory because the missing object is neither an exotic particle nor a remote galaxy. It would be another world within our own solar system, possessing its own geology, internal heat, atmosphere if one remains, and an unbroken history stretching across about 4,500,000,000 years. That possibility reshapes perspective. If the planet is finally found, the constellations above you will appear unchanged. The familiar motions of the planets will continue exactly as before. Earth's seasons will not shift. Oceans will not respond. Daily life will unfold without interruption. Yet, scientific understanding would gain an entirely new destination, another chapter in the architecture of our planetary family, and a deeper explanation for how that family assembled long ago. But every confirmed world expands the map we carry in our minds. Blank regions become inhabited places, assumptions give way to measurements. The solar system grows richer without becoming larger, because discovery changes knowledge rather than distance. Whether Planet 9 ultimately emerges from the darkness or dissolves beneath better evidence, the search reminds you and we that reality often announces itself long before it allows itself to be seen. Imagine unfolding the finest map your civilization can create. Every line has been measured with care. Every landmark carries a name. Then your eyes reach the margin, where certainty begins to fade. That boundary has always existed, and every generation has inherited a different version of it. The location changes, the experience does not. For ancient observers, the unknown began beyond the horizon where land and sky appeared to meet. During the great age of ocean voyages, it waited beyond coastlines that no chart yet described. Early astronomers believed the known planetary family ended with Saturn until Uranus expanded that frontier. Neptune carried it farther still. Later, the observable universe itself became another boundary, limited by the age of the cosmos and the finite speed of light. But every frontier behaved the same way. It never formed a permanent wall. Instead, it acted as a horizon, retreating whenever knowledge advanced. Each expedition uncovered territory that few expected, revealing patterns, structures, and questions hidden behind the previous limit. The farther we traveled, the more the map refused to remain complete. Today, our own frontier lies much closer than many people imagine. Beyond Neptune stretches a realm increasingly populated by discoveries, beginning with the Kuiper Belt and continuing through distant objects whose paths challenge familiar expectations. Sedna expanded our sense of the solar system's architecture. The Goblin added another unexpected piece. Other distant bodies continue to appear as observations accumulate, each contributing another fragment to a picture that remains unfinished. Certainty grows thinner there. Planet 9 occupies that uncertain margin. It does not represent the edge of the galaxy, nor the boundary of the universe, nor even the outermost extent of the sun's gravitational influence. Instead, it marks the present edge of confident knowledge inside our own celestial neighborhood. It is a question written onto a map that is otherwise becoming steadily more complete. But the people searching for that answer are following a remarkably familiar path. Their instruments differ from those of earlier explorers, yet the underlying task remains unchanged. They compare observations, test predictions, refine measurements, discard mistaken ideas, and continue forward. Every new survey extends the known landscape a little farther. Every improved telescope reduces another patch of uncertainty. Even unsuccessful searches reshape the map by showing where hidden worlds are not. What waits beyond today's boundary cannot yet be described with confidence. It may closely resemble current predictions. It may reveal structures no model presently anticipates. It may prove unexpectedly sparse. Whatever the outcome, the frontier itself will shift once more. You and we have inherited a moment when the map is still expanding, and that steady movement of the boundary, more than any single discovery, remains one of science's most enduring achievements. Shrink your view until our entire solar system becomes a tiny pattern drifting through a much greater landscape. The questions that once felt enormous begin to change their scale. They do not become less meaningful. They simply find their proper place within a universe that is almost beyond comprehension. Our sun is one ordinary star among an estimated 200 billion to 400 billion stars scattered across the Milky Way. That galaxy is only one among an estimated 2 trillion galaxies within the observable universe. Even the observable universe marks a practical horizon rather than a final boundary, defined by the finite age of the cosmos and the time light has had to travel since the beginning of cosmic expansion. Beyond that limit, the universe almost certainly continues, though no observation can presently confirm what lies there. Against such immensity, the possibility of a cold world circling our sun at between 400 astronomical units and 800 astronomical units, which is about 37 billion miles to 74 billion miles, seems like a remarkably local concern. But local is where every meaningful discovery begins. This search has never been about proving that our planetary family is unusually important. It has been about understanding the place that formed us. Every improvement to the map of our own celestial neighborhood deepens our understanding of the events that shaped Earth, the planets beside it, and the long history that made our existence possible. Perspective gives that effort its value. When we look outward, we are also looking inward, asking how this particular collection of worlds came together while countless others followed different paths. If Planet 9 exists, it becomes another chapter in that story. If it does not, the search still reshapes our understanding of how planetary systems evolve and how careful observation separates convincing patterns from coincidence. But perhaps the most remarkable feature has never been the unseen world itself. Consider what has unfolded on the third planet from this ordinary star. Roughly 4.5 billion years after Earth, condensed from interstellar dust and gas, living organisms emerged, evolved, developed language, mathematics, and instruments capable of measuring motions far beyond direct human perception. From those measurements came equations, predictions, and finally, the confidence to search for something no person has ever witnessed. That achievement was never inevitable. Nothing in the laws governing gravity required matter to become curious about itself. Nothing guaranteed that one species would eventually calculate the orbit of a possible unseen planet before seeing it with a telescope. Yet here you and we are, continuing that search together, using patience, imagination, and evidence to illuminate another small corner of an immense universe. Whatever answer ultimately arrives, it will belong to our home and to the enduring human habit of looking into darkness until it gradually becomes part of the map. Tomorrow's discoveries are already taking shape inside observatories that have only recently begun their work. Long before any announcement reaches the world, streams of fresh observations are flowing into computers where faint points of light are compared against images taken months and years earlier. Somewhere within those enormous archives, the next clue may already exist, waiting for enough evidence to separate it from countless ordinary stars. The Vera C. Rubin Observatory is expected to complete its first full survey of the visible sky during 2026 by about 2028. Its expanding catalog of distant solar system objects should provide enough statistical strength to test the unusual orbital clustering far more rigorously than any previous collection of observations. The uncertainty that has surrounded this question for years will steadily become smaller. But the search does not depend on one observatory alone. The Subaru telescope continues its careful examination of the northern sky, concentrating on the region near Orion, identified by refined orbital calculations. Every new observing season removes another portion of uncertainty. Every area that yields nothing remains scientifically valuable because it narrows the places where an unseen world could still be hiding. Another possibility remains equally intriguing. A smaller proposed planet, often called Planet Y, may reveal itself before Planet 9. Estimated to orbit between 100 astronomical units and 200 astronomical units, which is about 9 billion miles to 19 billion miles, it would be substantially closer to the Sun, and therefore easier for modern surveys to detect. Its existence could explain the unusual warp observed within parts of the distant Kuiper Belt, while opening an entirely different chapter in our understanding of the outer solar system. Future infrared space telescopes may extend that progress even further. By comparing observations separated by almost 4 decades instead of 2, astronomers could recognize extremely slow motion that earlier surveys struggled to distinguish from distant background sources. Patience becomes another scientific instrument. Within the coming decade, the evidence will likely guide us toward one of several outcomes. Planet 9 may emerge with a measured orbit and confirmed properties. The predicted planet may instead be ruled out, forcing entirely new explanations for the distant objects that first inspired the hypothesis. Or the growing catalog may redirect attention toward a refined model pointing somewhere unexpected. But one thing is already changing. The tools capable of answering this question are finally operating together. The search has entered a new stage where uncertainty is no longer limited by imagination alone, but by the steady arrival of better evidence. Far beyond Neptune, perhaps 500 astronomical units away, perhaps farther, an unseen traveler may still be following the same immense path it has traced for billions of years. Here, on one warm world only about 8 light minutes from the sun, you and we continue looking outward, adding one careful observation after another, trusting that patient curiosity remains one of the most reliable ways to transform darkness into understanding.